Create a tabular function for the stage duration as shown here. Select none for both hazard and probability for the interpolation transforms to interpolate linearly. The stage duration is the primary hazard for a seismic failure mode. Next, we need to calculate seismic weights so we can build out the event tree. The AEPs are the PGAs that define the system response, and the midpoints between those points have already been given to us and were obtained by interpolating from the seismic hazard, which is the secondary hazard in this analysis. To get the first probability, subtract the AEP for a PGA of 0.125 G from the AEP for a PGA of 0.05 G. The SRP at a PGA of 0.05 G is 0, so there is no need to consider anything less than a PGA of 0.05 G. Next, subtract the AEP for a PGA of 0.325 G from the AEP for a PGA of 0.125 G. Then subtract the AEP for a PGA of 0.565 G from the AEP for a PGA of 0.325 G. And finish by setting the last probability equal to the AEP of a PGA of 0.565 G. The computed probabilities are shown here. Back in RMC total risk, we need to add our event tree to compute the system response. Choose the seismic category, then select embankment deformation. That will give us this tree to start with. The next step is to pull in the reservoir stages to evaluate. Copy those stages from the example file. Click on the fan icon next to the reservoir stage and paste those values in under the hazard level. Now is also a good time to set the interpolation transform. We want semi-log interpolation, so the hazard transform will be none and the probability transform will be logarithmic. Next, branches need to be added for each of the 4 PGAs evaluated. Click the green plus sign to add 3 new branches, such that there is one for each of the 4 PGAs evaluated and one for the remainder, which captures the probability of a PGA less than 0.05 G. Rename each branch in the Properties window, 1 PGA per branch. To finish building out the tree, hover over the red node coming off the first PGA and click Copy All Branches to Clipboard. Hover over the red nodes for the PGAs below and click Paste to build out the rest of the event tree structure. Again, we are copying the set of branches coming off the 0.05 G branch and pasting it in for all following PGA branches. Assign a deterministic probability for each PGA branch. The probabilities will come from the seismic hazard partition and weights that we calculated earlier. From here, copy and paste the node data for each branch of the tree. There are a lot of branches, so take your time and be methodical. Be careful to make sure the probabilities are matched with the correct event tree branch. Once all the data is in, the system response plot should look like this. The next step is to pull in the life loss data using tabular and composite functions like we did in the first example. The correct composite non-breach life loss will look like this. And the correct composite breach life loss will look like this. From here, build out the simple risk diagram. The hazard will be the stage duration, which will connect to the non-breach consequences, and then the deformation system response and that failure mode's associated consequences. After running the analysis with full uncertainty, we get this FN scatter plot. And this loss exceedance or big FN plot. Be careful, however, because the background risk that comes from this analysis is not correct and should be ignored. The connection between the stage duration and the non-breach life loss in the risk diagram was needed to compute the incremental consequences, but cannot be used to create the non-breach risk. The non-breach risk must be a function of stage frequency, not stage duration. As such, the total or residual risk that is reported will also be incorrect. To get the correct non-breach risk, create a new tabular hazard for the stage frequency. And paste in the data from the example file. The uncertain value is probability, and the distribution will be PERT percentile Z. Then add a new risk analysis for the non-breach that simply ties the stage frequency hazard we just created to the non-breach consequences. Running this analysis will give us the correct plot for the non-breach or background risk. The residual risk unfortunately cannot be plotted using this version of total risk when seismic failure modes are involved. For this example, it can be done with some post-processing, but it is a lot of work. The failure FN pairs from the seismic failure mode need to be combined with the non-breach risk pairs to create the residual loss exceedance curve.